Most objects that we deal with don't have electric charges. However, as we have seen in the demonstration with rubbing a balloon on hair, an object like the balloon can obtain an electric charge. Where does it come from? In nature, electric charges don't just appear or disappear. However, they can be transferred from one object to another. In the case of rubbing a balloon on hair, what actually happens is that the balloon that is initially electrically neutral, that is, does not have an electric charge, gets some negative electric charge from hair. But the hair is also normally electrically neutral. So where does the negative electric charge come from? It turns out that all objects made of ordinary matter have both positive and negative electric charge inside them. However, an object is overall electrically neutral if the amounts of positive and negative electric charge that is present inside it are the same. When you rub a balloon on hair, it grabs some extra negative charge. So now the balloon has more negative charge than it has positive charge, and is overall negatively charged. Conversely, the hair gives up some of its negative charge to the balloon, so it now has less negative charge than it has positive charge, so it is overall positively charged. But where exactly does the positive and negative charge reside in objects that are made of ordinary matter? We said that ordinary matter consists of atoms and that atoms are electrically neutral. Therefore, it's logical to conclude that the positive and negative charges reside somewhere inside atoms. This conclusion turns out to be correct. The negatively charged electrons that J.J. Thomson discovered are indeed found inside atoms. However, that means that in order for atoms to be overall electrically neutral, they must contain an equal amount of positive charge. Furthermore, because electrons are so much lighter than atoms, the positively charged matter inside the atom must also be responsible for most of the atom's mass. Initially, J.J. Thomson speculated that the structure of an atom might resemble that of plum pudding. Most of the space inside plum pudding is occupied by dough, and the dough is responsible for most of its mass. Inside the dough, here and there are plums. Similarly, Thomson thought the bulk of the atom might be made up of positively charged matter, and the electrons may be located somewhere inside it. It was just a guess, a hypothesis. To determine whether it was correct, experiments needed to be carried out. In 1911, another British physicist, Ernest Rutherford, designed an experiment to test J.J. Thomson's idea. His experiment used alpha particles. Right now, we don't need to know exactly what they are. Let's just say that they are particles smaller than atoms that are produced in radioactive decay. The alpha particles were shot at a very thin piece of gold foil. Because the alpha particles were small and moved quickly, it was expected that they would go right through the piece of gold foil, like a bullet goes through a piece of paper. This is indeed what happened to most particles, but not to all of them, as explained in the following clip.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounced right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounced off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of two kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
So in conclusion, most of the mass of an atom is concentrated in its nucleus, that is approximately 100,000 times smaller than the atom itself, and is located at its center. Around the nucleus are electrons, but we can't know exactly where. Most of the space inside the atom is empty. If you are surprised that despite having all this empty space inside, the atoms don't go right through each other, think of the following analogy. A cage made of metal wire also has mostly empty space inside. However, two cages can't pass through each other. Like the wire that forms the cage, electrons in an atom provide enough resistance to stop other atoms from passing through. As scientists delved ever deeper into the structure of matter, they discovered that the atomic nucleus itself consists of two types of particles. Both of these particles are approximately 1,800 times heavier than the electrons. Their masses are similar and are almost the same as the mass of a hydrogen atom. One of these particles, the proton, has a positive electric charge. The other, the neutron, has no electric charge. The importance of this discovery lies in the fact that the atoms of different chemical elements differ in the number of protons in their nuclei. For example, all hydrogen atoms have only a single proton in their nucleus. All helium atoms have 2 protons, all lithium atoms have 3 protons, and so on. The number of protons in the nucleus determines the type of an atom. In other words, the atom of which chemical element it is. In chemistry, the number of protons in the nucleus of an atom is referred to as the atomic number. The number of neutrons in the nuclei of different atoms of the same chemical element, on the other hand, can vary. For instance, most hydrogen atoms only have one proton in their nucleus and they don't have any neutrons. However, a small percentage of hydrogen atoms, about 0.01%, have one proton and one neutron in their nuclei. This variety of hydrogen atoms, called deuterium, is about twice as heavy as regular hydrogen, called protium. However, it is still the same chemical element, hydrogen, because it also has only one proton in its nucleus. In fact, some hydrogen atoms can even have one proton and two neutrons. This variety is called tritium. The amount of naturally occurring tritium is extremely small, but it can be produced artificially. Tritium is approximately 3 times heavier than protium, but it is still the same element, hydrogen, because it also has only one proton in its nucleus. Atoms of the same chemical element with different numbers of neutrons in the nucleus are called isotopes. For instance, protium, deuterium, and tritium are all isotopes of hydrogen. Most elements have more than one naturally occurring isotope. However, the number of neutrons in an atomic nucleus is usually close to the number of protons for naturally occurring isotopes of lighter chemical elements. In heavier elements, there are deviations from this trend. We will talk about the reason why the chemical identity of an element is determined by the number of protons only and not by the number of neutrons later in the course. Just remember it for now. The magnitude of a proton's positive electric charge is the same as the magnitude of an electron's negative electric charge. Because atoms are overall electrically neutral, the number of electrons circling the nucleus of an atom must be the same as the number of protons in the nucleus.